Hello everyone. Today we'll study inverse functions. First of all, let me introduce one-to-one function. Let f be a function from a to b, written as f from a to b. If for every s1, s2 in A, here A is called domain. For every s1, s2 in A in the domain, f of s1 equal to f of s2 implies s1 equal to s2. Then we say f is one-to-one. What does it mean? Let's think of this. When we graph function f in the xy plane, usually we consider y equal to f of x. So f of s1 equal to f of s2 we can consider as for all points of the graph, whenever the y coordinate is the same, the s coordinate must also be the same. For all points on the graph, whenever the y coordinate is the same, the s coordinate must also be the same. It also means for every y in a range, there's exactly one corresponding x in the domain. For every y in the range, there exists exactly one corresponding x in the domain. That's what one-to-one means. If for some y, we find two corresponding x, then the function is not one-to-one. Next, let me show you an example. For each of the following functions, determine whether it's one-to-one. First example, f of x equal to 2x cubed plus 5. Is this function one-to-one? Let's set up like this. Assume f of s1 equal to f of s2. Assume f of s1 equal to f of s2. F of s1, we plug in s1 for each x. You get 2s1 cubed plus 5. For f of s2, I plug in s2 for x. I get 2s2 cubed plus 5. We try to prove s1 equal to s2. If I can prove s1 equal to s2, then the function is one-to-one. Otherwise, it's not one-to-one. Let's try. What we can try here is I can subtract 5 from both sides. I get 2s1 cubed equal to 2s2 cubed. Next, I can divide both sides by 2. I get s1 cubed equal to s2 cubed. Next, I can take cube root on both sides. If I take cube root on both sides, cube root cancel power 3. I get s1 equal to s2. Since I prove s1 equal to s2, then function f is one-to-one. Sometimes we write one-to-one like this, one-to-one. Function f is one-to-one. Another example, f of x equal to s squared plus 4. Is this function one-to-one? Try the same thing. Assume f of s1 equal to f of s2. We try to prove s1 equal to s2. If we can prove s1 equal to s2, then function f is one-to-one. Otherwise, it's not one-to-one. So assume f of s1 equal to f of s2. For f of s1, I plug in s1 for x. I get s1 squared plus 4. For f of s2, I plug in s2 for x. I get s2 squared plus 4. Next, I can subtract 4 from both sides. I get s1 squared equal to s2 squared. Next, I can take square root on both sides. When I take square root, be very, very careful. When we take square root, what happens? When we take square root, we must always add plus or minus sign. When we take square root, we must always add plus or minus sign. So, if I take square root, s1 equal to plus or minus s2. It doesn't guarantee s1 equal to s2. So, we can prove it like this. This function f is not one-to-one. We can prove it like this. To show a function is not one-to-one, try to show that there exists 2x which map to the same y. There exists 2x which map to the same y. Or we can say there is a y which has two corresponding x. Try to show that there is a y which has two corresponding x. Or there are two x that map to the same y. So let's try. We know that For x squared, if I plug in positive 1 or negative 1, we get exactly the same value. So I can let s1 equal to 1 and s2 equal to negative 1. There are two different x. If I plug in s1, f of s1 equal to f of 1, which is 1 squared plus 4, that's 5. F of s2, that's f of negative 1. Again, negative 1 squared plus 4, which is also 5. So f of s1 equal to f of s2. But s1 doesn't equal to s2. So f is not 1 to 1. That's how I prove a function is not 1 to 1. To prove a function is not 1 to 1, we can prove it like this. And to give an example, show that there are 2x, there exists 2x, which maps on the same y. Next, let me show you a graph for each function that will make more sense to you. The first function is f of x equal to 2x to the power 3 plus 5. If I graph this function in the calculator, the graph looks like this. If I graph this function in the calculator, the graph looks like this. The second function is x squared plus 4. That's a parabola open upward. In the calculator, it looks like this. That's the graph of the functions. In the first graph, we can see that for every y, there's only one x. For every y, there's only one corresponding x. For every y in the range, there's only one corresponding x. You only cross the curve once. For every y in the range, there's only one corresponding x. So this function is 1 to 1. This is a 1 to 1 function. Let's look at the second graph. For some y here, we can find two corresponding x here. For some y here, we can find two corresponding x, s1, s2. For some y here, we can find two corresponding x, s1, s2. Here, f of s1 is y. F of s2 is also y. But s1 doesn't equal to s2. So this function is not 1 to 1. So if we know the graph, in order to test if a function is 1 to 1, we can use horizontal line test. Horizontal line test says that if no horizontal lines cross the graph of the function more than once, then the function is 1 to 1. If no horizontal line cross the graph of the function more than once, then the function is 1 to 1. However, if some horizontal line cross the graph more than once, then the function is not 1 to 1. If some horizontal line crosses the function more than once, then the function is not 1 to 1. That's called horizontal line test. Next example. F of x equal to x cubed minus x minus 2. F of x equal to x cubed plus x plus 2. Are they 1 to 1? So, if we try to use the definition, to prove a function is 1 to 1, it looks very hard. We can try. It looks very hard. If we assume f of s1 equal to f of s2, and we try to show s1 equal to s2, that's very hard here. For f of s1, I plug in s1 for each x. I get s1 cubed minus s1 minus 2 equal to s2 cubed. I plug in s2 for each x. Minus s2 minus 2. I can add 2 to both sides. Make s1 cubed minus S1 equal to S2 cube minus S2. Then how can we show S1 equal to S2? We can try to bring everything over. Bring everything to one side. Make the other side 0. So I bring S2 cube over, make it negative. I bring S2 over, it's negative, I make it positive. Then factor, I get S1. Factor by grouping. For the first two terms, I got S1 minus S2 times S1 squared plus S1 S2 plus S2 squared. Then for the second half, I pull out negative 1. I get S1 minus S2 equal to 0. Then pull out common factor S1 minus S2. I get S1 minus S2 times S1 squared plus S1 S2 plus S2 squared minus 1 equal to 0. If I factor this out, that's what's left. Then solve an equation. If we solve the first equation, we know S1 equal to S2. But how do we know there's no solution here? It may be some other solution from here. So it's hard to tell by using definition. It's hard to prove this function is one-to-one using definition. It's hard to tell whether this is a solution or there's a solution or not. There may be another solution. If there's no solution here, then we prove S1 equal to S2. That shows that F is one-to-one. However, if there's a solution here, then there's no guarantee that S1 equal to S2. That means the function is not one-to-one. But it's very hard to solve this equation here. So to prove this function using definition is very hard. To prove this function is one-to-one using definition is very hard. So another choice for us is the graph. Another choice for us is to use graph. If we graph the function in the calculator, the graph looks like this. If I graph this function in my calculator, I get this graph. I can tell that this function is not one-to-one. It doesn't pass horizontal line test. Here you can see that this horizontal line crosses the curve more than once. It doesn't pass horizontal line test. This function is not one-to-one. So in the calculator, I find that f of 0 equal to 0 cube minus 0 minus 2 equal to negative 2. F of 1 equal to 1 cube minus 1 minus 2, which is also negative 2. Since 2x maps to the same y, this function is not one-to-one. Now, how about this function? If we graph this function in the calculator, I get some graph like this. And if I use horizontal line test, I can see that every horizontal line crosses the curve once. No horizontal line crosses the curve more than once. So based on this graph, the function seems to be one-to-one. However, do we have enough evidence to say this function is one-to-one? Be very, very careful. When we graph a function in the calculator, we only see the graph in a very, very small window. When we graph this function in the calculator, we only see this graph in a small window. In the calculator, we only see this graph in a very, very small window. In a very, very small window. we don't really know what happened to the graph outside the window. We don't know what happened to the graph outside the window. So, based on this graph, there's not enough evidence to say this function is one-to-one. Based on the graph in a small window, there's not enough evidence to say this function is one-to-one. But how can we show this function is one-to-one? In order to show a function is one-to-one, we can use derivative test. In order to show a function is one-to-one, we can use derivative test. The derivative test says that let f be a continuous and differentiable function defined on an interval. If the derivative f prime of x is always positive or always negative, then function f is one-to-one. So, if f prime is always positive, that means the function is increasing. If the function is increasing, it passes horizontal line test. Every horizontal line crosses the curve, no more than once. So the function is one-to-one. If the derivative is negative, then the function is decreasing. You also pass horizontal line test. Every horizontal line crosses the curve, no more than once. So if the derivative is always positive or always negative, then the function is one-to-one. That's called the derivative test. If I take derivative here, f prime of x is 3x squared plus 1. If I take derivative for function f prime of x is 3x squared plus 1. Is this function always positive? We know that s squared is always greater or equal to 0. S squared is always positive. So 3 times s squared is always greater or equal to 0. When I add 1, 3x squared plus 1 is always greater or equal to 1, which is strictly greater than 0. Since f prime of x is greater than 0 for all x, then f is one-to-one. Function f is one-to-one by derivative test. So in general, we use derivative test to show a function is one-to-one. And we use horizontal line test to show a function is not one-to-one. In general, we can easily use horizontal line test to tell a function is not one-to-one. And to show a function is one-to-one, usually we use derivative test. Next, let me introduce inverse function. If f from a to b is one-to-one, then f has an inverse function, denoted by f inverse. F inverse is a function from the range of f. R sub f represents the range of f. Inverse of f is a function from range of f to a. From range of f to a. Range of f is a subset of b. Inverse of f is a function from the range of f to a, such that f inverse of y equal to x whenever f of x equal to y. Next, let's look at an example. Let f of x equal to 2x cubed minus 10. Show that f is one-to-one. Then find f of 3 and inverse f of 44. First of all, show that f is one-to-one. Then find f of 3 and f inverse of 44. How can we show f is one-to-one? To show f is one-to-one, we can try to use derivative test. If I take derivative f prime of x, I get 6x squared. Is this function always positive? Is f prime always positive or always negative? We know that 6x squared is always greater than or equal to 0. There's no guarantee this function is always greater than 0. It's greater than or equal to 0. So, using derivative test is not enough to say the function is one-to-one, because f prime of x is greater than or equal to 0. In order to say the function is one-to-one, we must show that f prime of x is strictly greater than 0. Here, since f prime of x is greater than or equal to x, we can use directive test to show the function is one-to-one. So it doesn't work. We must use the definition of one-to-one function to show f is one-to-one. So let's use definition. Assume f of s1 equal to f of s2. That means 2s1 cube minus 10 equal to 2s2 cube minus 10. I can first of all attend to both sides. If I attend to both sides, I get 2s1 cube equal to 2s2 cube. Then I can divide both sides by 2. If I divide both sides by 2, I get s1 cube equal to s2 cube. Then I can take cube root on both sides. If I take cube root on both sides, cube root cancel power 3. I get s1 equal to s2. So f is one-to-one. So in general, if the directive test doesn't work, we need to use definition of one-to-one function to show f is one-to-one. Next, find f of 3. How do we find f of 3? For f of 3, we plug in 3 for x. So f of 3 equal to 2 times 3 cube minus 10. 3 cube is 27. 2 times 27 is 54. 54 minus 10 is 44. So f of 3 is 44. Next, find f inverse of 44. What's f inverse of 44? What's f inverse of 44? We know that for inverse function, f inverse of y equal to x whenever f of x equal to y. So if f take x, if f map x to y, f inverse function map y back to x. The inverse function of f map y back to x. So f map 3 to 44. That means inverse function of f map 44 back to 3. So f inverse of 44 equal to 3. Next example. Let f of x equal to square root of 3x plus 10 plus 100. Show that f is one-to-one. Then find f of 0 and inverse f of 10. So how can we show f is one-to-one? We can try to use directive test. But the thing is, taking derivative for a radical function is not easy. So let's use definition of one-to-one function to show this function is one-to-one. Taking derivative for radical function is not easy. So let's use definition of one-to-one function to show this function is one-to-one. Assume f of s1 equal to f of s2. I plug in s1 for x, and then I plug in s2 for x. I get square root of 3s1 plus 100 equal to square root of 3s2 plus 100. Then I can square both sides. If I square both sides, I get 3s1 plus 100 equal to 3s2 plus 100. If I square both sides, square cancel square root, I get 3s1 plus 100 equal to 3s2 plus 100. Next, I can subtract 100 from both sides. If I subtract 100 from both sides, I get 3s1 equal to 3s2. Next, I can divide both sides by 3. If I divide both sides by 3, I get s1 equal to s2. Since f of s1 equal to f of s2 implies s1 equal to s2, that means f is one-to-one. Next, find f of 0 and f inverse of 10. For f of 0, I plug in 0 for x. That's square root of 3 times 0 plus 100. 3 times 0 is 0. 0 plus 100 is 100. So we get square root of 100. Square root of 100 is 10. So f of 0 equal to 10. F of 0 equal to 10. Next, find f inverse of 10. What's f inverse of 10? We know that f inverse of y is x whenever f of x is y, which means function f take x to y, then inverse f take y back to x. So f map 0 to 10. Inverse of f map 10 back to 0. So f inverse of 10 is 0. Next, let me show you how to find inverse functions. For each of the following functions, find its inverse function. F of x equal to 4x cubed minus 1. How do we find the inverse function? In order to find the inverse function, I first of all replace f of x with y. Then solve an equation for x. Try to get x by itself. I can first of all add 1 to both sides. I get y plus 1 equal to 4x cubed. Then I can divide both sides by 4. I get y plus 1 over 4 equal to x cubed. Next, I can take cube root on both sides. I get y plus 1 over 4 equal to x. Once I get x by itself, interchange x and y. I get cube root of y plus x plus 1 over 4 equal to y. Interchange x and y. And then, what's left here? This is the inverse function. Once I get y by itself, what we have here is the inverse function. So inverse f of x is cube root of x plus 1 over 4. That's how we find inverse function of f. Next example, f of x equal to s plus 2 over 2s plus 1. Find the inverse function. So first step, replace f of x with y. Then solve the equation for x. I can write y as y over 1. I can first of all write y as y over 1. Then cross multiply. I get y times 2s plus 1 equal to 1 times s plus 2. Then distribute. I get 2sy plus y equal to s plus 2. Since we are solving for x, so move x to the left side. Everything else go to the right side. So move x to the left side. I get 2sy minus x. Move y to the right side. I get 2 minus y. Then factor s out. If I power x, I get 2y minus 1 equal to 2 minus y. Next, I can divide both sides by 2y minus 1. S equal to 2 minus y over 2y minus 1. Once I get s by itself, interchange x and y. I get y equal to 2 minus x over 2s minus y. Once we get y by itself, once I interchange x and y equal to y equal to inverse of x. Once I interchange x and y equal to inverse of x. So that's inverse of x. 2 minus x over 2x minus 1. Next example. F of x equal to x squared minus 6x, where x is greater than or equal to 3. For the inverse function, first step, replace f of x with y. I get y equal to x squared minus 6x. Next, try to solve an equation for y. This is a quadratic equation, so I can try to complete square. X squared minus 6x, the middle coefficient here is negative 6. In order to complete square, I take negative 6 divided by 2, which is negative 3. Then, take negative 3 square, which is 9. Take the middle coefficient, negative 6 divided by 2. Then, square the number, I get 9. Add 9 to both sides. In order to complete square, add 9 to both sides. I get y plus 9 equal to x squared minus 6x plus 9. Here, the right side is a perfect square. If we factor the right side, it's a perfect square. If we factor the right side, we get x minus 3 times x minus 3. Find two numbers, then multiply to be 9, add to be negative 6. That's x minus 3 times x minus 3. And when we see x minus 3 times itself, we write x minus 3 squared. When we see x minus 3 times itself, we write x minus 3 squared. On the right side, on the left side, leave it the way it is. Next, I can take square root on both sides. When I take square root, I need to add plus minus sign. Now here, is it plus or minus? As a function, it cannot be both plus or minus. As a function, it cannot be both plus or minus. Is it positive or negative? Look at here. According to what's given, x must be greater than 3. That's the domain. If x is greater than 3, that means x minus 3 must be greater than 0. If x is greater than 3, then x minus 3 must be greater than 0. So x minus 3 here must be positive. Since it's greater than 0, it must be positive. So x minus 3, it must be positive. Square root of y plus 9. Then I can add 3 to both sides. I get s equal to square root of y plus 9 plus 3. Once I get s by itself, interchange x and y. Once I get s by itself, interchange x and y. I get y equal to square root of x plus 3 plus 9 plus 3. And after I interchange x and y, the function here is inverse function. The function here is inverse function of f. So inverse function of f is square root of s plus 9 plus 3. That's inverse function of f. Next example, graph the function f of x equal to x squared minus 6x for x is greater than or equal to 3, and its inverse function square root of x plus 9 plus 3 in the same coordinate plane. Let's graph the function. How can we graph the function x squared f of x equal to x squared minus 6x? This is a parabola open upward. This is a parabola open upward. The s-intercept, if I set equal to 0, s-intercept is 0 and 6. If I set equal to 0, s-intercept is 0 and 6. The graph is a parabola open upward. The graph is a parabola open upward. What's the vertex here? What's the vertex? The graph is a parabola open upward. What's the vertex? Vertex is in the middle of these two intercepts. 0 and 6, the midpoint is 3. vertex locate at this line here. If I plug in 3 for x, 3 squared is 9. 6 times 3 is 18. 9 minus 18 is negative 9. So that's the vertex. The graph is a parabola open upward. That's the vertex. We only have half of the parabola because only graph on the part that x is greater than or equal to 3. So that's the graph. Y equal to f of x. That's the graph. It terminates at 3. We only graph on the part x is greater or equal to 3. That's the graph. Y equal to f of x. Next, how can we graph the inverse function here? For the inverse function, we can graph it using transformation. We know that y equal to square root of x. The graph looks like this. When I add 9 to x, I shift the graph 9 units to the left. When I add 9 to x, I shift the graph 9 units to the left. Shift the graph 9 units to the left. Then when I add 3 to the function, I shift the graph 3 units upward. So shift this graph 9 units to the left and 3 units upward. That's the graph. Y equal to inverse of x. Y equal to f inverse of x. So that's the function. That's the graph of f. That's the graph of inverse of f. If we observe these two graphs, we can see that. They are symmetrical over the line. Y equal to x. They are symmetrical over the line. Y equal to x. They are symmetrical over the line. Y equal to x. If I flip the graph over, y equal to f of x over the line y equal to x, I get a graph of inverse of the inverse of f. If I flip the graph of f over the line y equal to x, I get a graph for inverse of f. So they are symmetrical over this line y equal to x. So note, the graph of inverse of f is always the reflection of f the reflection of the graph of f over the line y equal to x. The graph of inverse of f is always the reflection of function f over the line y equal to x. Next, let me introduce a theorem. If f is a continuous one-to-one function defined on an interval, then its inverse function f inverse is also continuous. Think of this. The graph of f inverse is always the reflection of the graph of function f. Then, if f is continuous, f inverse must also be continuous, since the inverse function is always the reflection of function f. If function f is continuous, then the inverse function is also continuous. Next, let me introduce the property of inverse functions. Let f from a to b be a one-to-one function. Then f inverse exists, and f inverse of y equal to x whenever f of x equal to y. So observe these two equations here. If I replace this y with f of x, what do we get? We know that y equal to f of x. If I replace this y with f of x, what do we get? If I replace this y with f of x, in this equation, if I replace y with f of x, I get f inverse of f of x equal to x. In this equation, if I replace y with f of x, I get f inverse of f of x equal to x. So f inverse of f of x equal to x. That's one property of inverse function. That's one property of inverse function. F inverse of f of x equal to x for all x in the domain. We can consider f inverse cancel function f. We get s by itself. We can consider here f inverse cancel function f. We get s by itself. And similarly, f inverse of x equal to y, whenever f of y is x. F inverse of x equal to y, whenever f of y is x. If I replace this y in this equation here, if I replace this y with f inverse of x, because y equal to f inverse of x, if I replace this y with f inverse of x, what do I get? In this equation, replace y with f inverse of x, I get f inverse of x equal to x. In this equation, replace y with f inverse of x. Replace y with f inverse of x. I get f of f inverse of x equal to x. So f of f inverse of x equal to x. We can also consider f cancels f inverse. We get s by itself. F of f inverse of x. F and f inverse can cancel. We get s by itself. So f of f inverse of x equal to x for all x in a range of f. F of f inverse of x equal to x for all x in the range of f. Those are two properties of inverse function. Keep it in mind. Whenever we have f and f inverse together, consider they get cancelled. Okay, consider they get cancelled. We get whatever inside by itself. When we have f and f inverse together, consider they get cancelled. We have what's inside by itself. Next example. In the previous example 2, we know that f of x is x plus 2 over 2s plus 1. And f inverse of x is 2 minus x over 2s minus 1. Verify that f inverse of f of x is x, and f of f inverse of x is also x. Let's verify the first equation first. F inverse f of x. We plug in f of x into inverse of x. Plugging f of x into inverse of x. Plugging f of x into inverse of x. When I plug in the inverse function here, replace each x with f of x. I get 2 minus s plus 2 over 2s plus 1 over 2 times s plus 2 over 2s plus 1 minus 1. In the inverse function, replace each x with f of x. That's what we get here. Then simplify. Observe the numerator and denominator. We can see that the common denominator here is 2s plus 1. 2s plus 1 is the common denominator. So I can first of all multiply top and bottom by 2s plus 1. If I multiply top and bottom by 2s plus 1, I distribute 2s plus 1 to both terms in the numerator and both terms in the denominator. So I get 2s plus 1 times 2 minus 2s plus 1 times this fraction. When I take 2s plus 1 times this fraction, it cancels the denominator. When I take 2s plus 1 times this fraction, it cancels the denominator. What's left is s plus 2. That's the numerator. Next, I can distribute this to the denominator, to both in the denominator. When I multiply 2s plus 1 to the first fraction here, it cancels the denominator. When I multiply this to the first fraction here, it cancels the denominator. What's left is the numerator. So we get 2 times s plus 2. Then I distribute this, I multiply this to number 1. I get 1 times 2s plus 1. Next, simplify. Distribute 2, I get 4x plus 2 minus x minus 2. In the denominator, distribute 2. We get 2s plus 4 minus 2s minus 1. Then combine like terms on the numerator and denominator. On the top, if I combine like terms, I get 3x. Positive 2, negative 2 cancel. In the denominator, 2x and negative 2x can cancel. 4 minus 1 is 3. 3x over 3 is x. So I verify the first equation. F inverse of f of x is x. Next, verify the second equation. F of f inverse of x is x. For f of f inverse of x, I first of all plug in f inverse of x here. F inverse of x is 2 minus x over 2s minus 1. I plug in f inverse of x into function f. Replace each x with f inverse of x. Replace each x with f inverse of x. I get 2 minus x over 2s minus 1 plus 2 over 2 times 2 minus x over 2s minus 1 plus 1. Replace each x with f of x. In function f, replace each x with f of x. Then simplify. If we observe the fraction here, we can see that from the top and the bottom, the common denominator is 2s minus 1. The common denominator is 2s minus 1. So I can multiply 2s minus 1 to both the numerator and denominator. If I multiply 2s minus 1 to the top and the bottom, I need to distribute 2s minus 1 to every term on the top and every term on the bottom. If I distribute 2s minus 1 to the first fraction, it cancels the denominator. What's left is 2 minus x. If I multiply 2s minus 1 to 2, I get 2 times 2s minus 1. If I multiply 2s minus 1 to the first fraction here, it cancels the denominator. I get 2 times 2 minus x. If I multiply 2s minus 1 to the second fraction, to the second term, I get 1 times 2s minus 1. Then distribute and combine like terms. I get 2 minus x. If I distribute 2, I get 4s minus 2. For the denominator, if I distribute 2, I get 4 minus 2x plus 2x minus 1. Then combine like terms on the numerator and denominator. On the top, 2 minus 2 can cancel. Negative x plus 4x is 3x. That's the numerator. In the denominator, negative 2x and positive 2x can cancel. What's left is 4 minus 1. And we know that 4 minus 1 is 3. 3 can cancel, we get x. So we verify the second equation. F of f inverse of x is always x. So those are the property of inverse functions. F inverse of f of x is always x. F of f inverse of x is also x. When we see f and inverse f together, they can cancel. What's left is whatever inside the parentheses. When we see f and inverse f together, they can cancel. What's left is what's in the parentheses. That's the property of inverse function. Next, let me show you a theorem. Let f be a one-to-one function with inverse function f inverse. If f is differentiable, then whenever f of f inverse of a is not 0, f inverse is differentiable at a with f inverse prime of a equal to 1 over f prime of f inverse of A. How can we prove it? We try to prove left side equal to the right side. What's f inverse prime of A? We know that the definition of limit says f prime of A equal to the limit s approach to A, f of x minus f of A over s minus A. That's the definition of derivative. If we apply the definition of derivative here, we get limit s approach to A. Here the function is f inverse. So I have f inverse of x minus f inverse of A over s minus A. By definition of derivative, that's what I get here. Next, if I let y equal to f inverse of x and b equal to f inverse of A, if I let y equal to f inverse of x, let b equal to f inverse of A, how can I rewrite this equation? If y is f inverse of A, if y is f inverse of x, that means x equal to f of y. If b equal to f inverse of A, that means a equal to f of b. Also, since f is differentiable, f must be continuous. Since f is differentiable, f is continuous. If f is continuous, its inverse function is also continuous, because the inverse function is a reflection of function f. So f inverse is also continuous, because the graph of f inverse is a reflection of function f over the line y equal to x. Because the graph of an inverse function is a reflection of function f over the line y equal to x. So if f of x is continuous, its inverse function is also continuous. Since f inverse is continuous, so when s approach to A, we have f inverse of x approach to f inverse of A. Since the function f inverse is continuous, when s approach to A, f inverse of x also approach to f inverse of A. That's what we have here. Hence, f inverse of x is y. F inverse of A is b. Hence, y approach to b. Hence, when s approach to A, y approach to b. So, the above limit can be rewritten as s approach to A, y approach to b. As s approach to A, y approach to b. F inverse of x is y. F inverse of A is b. X is f of x. X is f of x. X is f of y. Sorry. X is f of y. Minus A. A is f of b. Then this limit can be written as limit. Since there's no more x, I can remove x. Since in the equation here there's no more x, I can remove x. So this limit can be written as limit as y approach to b. This fraction can be rewritten as 1 over the reciprocal. Any fraction can be rewritten as 1 over the reciprocal. For example, 2 over 3 can be rewritten as 1 over the reciprocal. Any fraction can be written as 1 over the reciprocal. Any fraction can be rewritten as 1 over the reciprocal. The same for this fraction, I can write it as 1 over the reciprocal. Reciprocal is f of y minus f of b over y minus b. Then this can be rewritten as 1 over the limit y approach to b, f of y minus f of b over y minus b. Since the function y equal to 1 over x is continuous, the function 1 over x is continuous, so I can bring limit inside. Since the function 1 over x is continuous, I can bring the limit inside. Then, what's this limit? If we compare this limit with this limit here, you can see that they are very, very similar. This match the definition of limit. This match the definition of derivative. This match the definition of derivative. This equal to 1 over f prime of b. This equal to 1 over f prime of b. This match the definition of derivative. That's y. That's f prime of b. And we know that b is f inverse of a. B is f inverse of a. So I get 1 over f prime of f inverse of a. Let's complete the proof of the theorem. Let's complete the proof of the theorem. Next, let me show you an example. Let f of x equal to x cubed plus 2x plus 6. Find f inverse prime of 9. How can we find f inverse prime of 9? According to the previous theorem, f inverse prime of a is 1 over f prime of f inverse of a. If I plug in 9 for a, I get 1 over f prime of f inverse of 9. So, find f inverse of 9 first. Find f inverse of 9 first. What's f inverse of 9? What's f inverse of 9? Let's take a guess. Let's take a guess. For f inverse of 9, let's think of this way. What can I plug into the function to make 9? What number should I plug into the function to get 9? Take a guess. What number should I plug into the function to get 9? Take a guess. If I plug in 1, what do I get? If I plug in 1 for x, what do I get? I get 1 plus 2 plus 6, which is 9. So, by guessing, we find out f of 1 is 9, which means f inverse of 9 must be 1. If f map 1 to 9, f inverse will map 9 back to 1. Since f of 1 is 9, f inverse of 9 is 1. So f inverse of 9 is 1. Next, find f prime of 1. Next, find f prime of 1. What's f prime? For f prime, we take derivative for function f. For f prime, take derivative for function f. Take derivative for function f. I get 3x squared plus 2. Then I plug in 1. I get f prime of 1. For f prime of 1, I plug in 1 into the derivative. That's 3 times 1 squared plus 2. 3 times 1 plus 2 5. So f prime of 1 is 5. That's the answer. That's the answer. So first step, I guess the number. Guess the number. When I plug in, I get 9. First step, guess the number. This is by guessing. We guess the number. When I plug in, I get this 9. That means f inverse of 9 equal to this number. Then find derivative. Take derivative. Plug the number in the parentheses. That's the denominator. That's the denominator. And this is the final answer. F inverse prime of 9 equal to 1/5. That's the final answer. Next example. Let f of x equal to sine 2x plus cosine x plus 4x. Find f inverse prime of 1. How can we find f inverse prime of 1? Think of the previous theorem. The previous theorem says f inverse prime of a is 1 over f prime of f inverse of a. So for f inverse prime of 1, I plug in number 1 for letter a. I get 1 over f prime of f inverse of 1. So here, solve the inner parentheses first. Solve the inner parentheses first. Try to find f inverse of 1 first. What's f inverse of 1? Think of this way. Take a guess. What should I plug into the function? What should I plug into the function to get 1? What should I plug into the function to get 1? Let's try some simple number. If I plug in 0, what do I get? If I plug in 0, what do I get? If I plug in 0, sine 0 is 0. Cosine 0 is 1. 4 times 0 is 0. 0 plus 1 plus 0 is 1. So by guessing, we know that if I plug in 0, I get 1. This 0 is by guessing. By guessing, I found a 0. When I plug in 0, I get 1. If f of 0 is 1, that means f inverse of 1 is 0. If f map 0 to 1, f inverse will map 1 back to 0. So f inverse of 1 is 0. So I have f prime of 0. I plug in 0 for f inverse of 1. Next, let's find f prime of 0. Let's find f prime of 0. Let's first of all find f prime of x. What's f prime of x? What's f prime of x? For f prime of x, take derivative for this function. Take derivative for sine 2x. I get cosine 2x. And then by chain rule, times 2. When I take derivative for cosine x, I get negative sine x. When I take derivative for 4x, I get 4. Then, plug in 0. Plug in 0 into the derivative. I get f prime of 0 equal to 2 times cosine 0. Cosine 0 is 1. Sine 0 is 0 plus 4. 2 times 1 is 2. 2 minus 0 is 2. And 2 plus 4 is 6. So f prime of 0 equal to 6. That's the denominator. I get 1 over 6. That's an answer to this problem. That's the final answer to this problem. 1 over 6. 6 is the denominator. Note, in the previous theorem, we know that f inverse prime of a equal to 1 over f prime of f inverse of a. If I replace a with x, what do I get? If I replace a with x, I get f inverse prime of x equal to 1 over f prime of f inverse of x. Next, if I let y equal to f inverse of x, if I let y equal to f inverse of x, then this equation can be rewritten as f inverse prime of x equal to 1 over f prime of y. If I let y equal to f inverse of x, this equation can be rewritten as f inverse prime of x equal to 1 over f prime of y. Also, y equal to f inverse of x, that implies x equal to f of y. Y equal to f inverse of x, that implies x equal to f of y. So, if I take derivative for y, dy over dx will be f inverse prime of x. If I take derivative of y with respect to x, dy over dx is f inverse prime of x. And if I take derivative of x with respect to y, if I take derivative of x with respect to y, I get ds over dy equal to f prime of y. If I take derivative with respect to y, I get dx over dy equal to f prime of y. Then, if I plug in to this equation, if I plug in dy over dx and ds over dy into this equation, f inverse prime of x equal to dy over dx. F inverse prime of x equal to dy over dx. And on the other side, f prime of y equal to ds over dy. So, keep this idea in mind. Dy over dx always equal to 1 over ds over dy. Dy over dx always equal to 1 over ds over dy. Keep this formula in mind.